Okay, so everyone, welcome to the first session of this first day. Now we will discuss about fragility analysis. The model. Yeah. Okay. Okay, so the moderator of this session will be me, with Dan, because I was presenting before, and now Dan is presenting, so of course I will be the moderator. So we will have a scribe, and the scribe will be Mohammed Alam. Okay, thank you, Mohammed, for serving to the scribe. So we will start with the first presentation given by Ruben Vescovo, who will present his work, the first presentation of this session. Ruben.
I guess I'll present myself again. I'm Ruben, and I'm going, as I said earlier, I'm going backwards. I kind of spoiled the end of the presentation earlier. Hopefully you didn't pay too much attention. I kind of spoke all over the place. I am a final student, final year PhD student at Tohoku University, mainly working with Bruno Adriano and Shinichi Kushimura, who are my two main supervisors. And I'll be talking about fragility estimates for tsunami and how we can quantify the data at the smallest possible scale. Is this the? Yep. Oh, cool. Fantastic. So first, let me go through a little bit of a background of what fragility functions are, and this is probably going to be a little bit boring for a lot of you because you probably know this inside out better than me. But fragility functions, much like PTHA and PTRA, are translated from earthquake engineering, and they are quantitative vulnerability models that try to link a hazard to a risk by taking an engineering demand parameter that is a measure of intensity of the disaster and relating it to the probability of reaching or exceeding a specific damage state. And they generally developed in an asset-specific fashion. So there's tsunami fragility functions for buildings, steel buildings, roads, boats. You can mention whatever you want, but I'll put some formal definitions on the board if you want to get into that a little bit. And rather than reading through these for history, I'd like to point out some of the, I guess, major innovations that have come from fragility functions and how they were introduced first, formalized in 2009 for tsunamis from kind of that earthquake engineering perspective. And this initial formulation used aggregated data with ordinal least squares, which is a statistical framework for modeling these exceedance curves. And it was in 2011 where we saw the first disaggregated model using the raw data and generalized linear models to fit that data. We have some adaptations later on for low data availability, and that was done for Chile, I believe, in the Chaco. I'm not sure if I'm getting this right. Finally, in 2013, we get some of the bigger data sets with the 2011 Tohoku earthquake. Supazri et al. Formulated 6 fragility functions for a whole lot of buildings, and this is probably one of the largest data sets we have for tsunami damage data. And finally, I guess, and this is where some of my work also gets inspired from, is we have some fragility functions that try to use probabilistic frameworks to account for input uncertainty using Bayesian inference and Bayesian machine learning. But I guess one of my biggest questions while I was trying to figure out where I was going with my PhD was, what are these fragility functions actually used for? Because in earthquake engineering, there's insurance, there's the global earthquake model that was mentioned as well this morning. But from our studies, the vast majority of fragility functions seems to be limited to academic discussion. Though it is hinted in this academic discussion that some of these models could be actually adapted into probabilistic frameworks. And I'll speak about this a little bit later. But some of the limitations of these fragility functions we found are that they seem to be, it seems to be hinted even in the literature that they warn against adaptability and whether you can bring a fragility function from one area to a different area and how that kind of propagates the uncertainty, because there is inherent uncertainty in your first domain. So how does that transfer to your second domain? And the second thing is fragility functions produce measures in aggregate. So you get a percentage of your whole population, and that's your loss, but you don't know what happens at the individual scale. So we think that's a bit of a shame. And some attempts have been made to try to curtail that and do some disaggregated measures, which I showed over there on the right. Well, my left and right. Confused. Yeah, and I put them in order with some of the authors here. The biggest problem with these adaptations is that we don't have ways of verifying them, especially for the first two from Supervisor Bruno and Roman and Cho for Korea. There is no ground truth for which we can quantify whether our measurements or our predictions reflect the truth. The only example we have of this is Luis Moya, who tried something like this, but it's an earthquake engineering example, so it's not really applicable to tsunami. Some efforts have been made to push the probabilistic framework and to fit fragility functions in kind of this from hazard to risk quantification models, but this is still in its infancy. I thought we had a little bit of a talk about the global tsunami model earlier, and hopefully we can learn some more from the poster later. But yes, we do believe that fragility functions can offer guidelines or inform policy and decision makers. However, as was mentioned this morning, we would kind of like some measure of concreteness when we communicate to stakeholders and even the community. And so this brings us to how do we get these damage maps done, and to what level of disaggregation can we get to, really? Because we have disaggregated measurements that come in from our tsunami data, or our tsunami models can give us, as Diego mentioned this morning, very fine probabilistic resolution at the coastline, and the inundation model can then take care of that. But how can we, instead of producing a fragility function and then aggregating the measures, can we do it at the building scale, and can we verify that? And so if we can do that, then we can also look at whether our models are adaptable, and how can we account for the uncertainty in these cases, because obviously if we don't use a probabilistic approach, then we kind of have just a snapshot measurement, but that doesn't tell us anything about how our uncertainty from the inputs transfers to the outputs. And so that brings us to some of our experiments, the first one of which is just a naive machine learning application for a classification framework, which we kind of used as a testing ground for whether we could actually do this. Is it feasible to predict damage using engineering demand parameters and measures of tsunami intensity? And can we do it so that we get something that's useful down the line and it's verifiable? And we use these demand parameters kind of to control the latent processing, as I mentioned in my 1-minute talk earlier. So, for example, our inundation doesn't have any kind of inclination towards whether the load on a building is the hydrostatic load or the hydrodynamic load. So we need some extra proxies to do that kind of calculation. So we include these kind of engineering demand parameters into our model to account for these proxies. And the goal is to make as many proxies as we can to account for as many latent proxies as we can. And these are some of our initial results from, and this is Ishinomaki City in Japan. We're using the Tsunami data set from 2011 to train and test our machine learning model. And the first two here on the left are the adaptations for the tsunami fragility function that were mentioned at the beginning. And the methods are the top one from Bruno, Adriano et al. And the second one is Moya's method, with the third one being our own, which is the machine learning model. And we can see that we have some interesting patterns here. I'll speak about this a bit. Yeah, okay, cool. So we have some more interesting, maybe I can point, spatial trends that we can learn with these demand parameters, but still we get a lot of mixing in the middle classes, which is not something we want. One limitation of classification frameworks is that they don't account for class ordering. And as tsunami engineers, we kind of know that, you know, your destroyed damage state comes after your less destroyed damage states. So it is important to find a framework that embeds these characteristics as well as the actual processes that we want, the physical processes that we want to model. And this brings us to a probabilistic approach. And this time we are able to impose this order by adopting an ordinal regression model, which is again just a generalized linear model, but using a Bayesian framework, we can tap into this huge knowledge bases of optimization, uncertainty quantification, decision-making processes that we can use to then analyze our results. And so we can place priors over our parameters to kind of give us an inclination of what our uncertainty is going into the model and how this propagates. It's a bit bright, actually, but hopefully you can make it out. Our precisions and our accuracies are much better here, and we're learning much nicer trends, especially around these areas which were much harder to predict inland, where we're getting less damage, and even here on the west side. Yes, so east side. Yes. And our uncertainty measures kind of reflect a little bit of what our hypotheses would have been for where our damage distributions are less certain, which is in the center, this middle class, where our predictions tend to be, our inundation levels tend to be much lower, and our predictions therefore tend to be quite mixed in terms of what kind of processes are actually affecting these predictions. Is it tsunami, is it earthquake? And so when our tsunami loads get much smaller, there's a lot more interesting stuff going on that we still can't seem to capture here. But this probabilistic approach kind of lets us investigate that a little bit better. And this is the same model applied to a completely different domain. This is the Noto Peninsula disaster. It's a little excerpt on the west side of the Noto Peninsula called Ukai. And we see here in our prediction that we get much of the tsunami trend. However, around the inland sections, we're still not capturing some of the damage here. And so, and in this case, the uncertainty kind of lies to us because it tells us that it's really, really quite certain of these predictions that it's telling us are survived, however they're damaged. And so we can look into that a little bit more. And our next slide, we can see that indeed it seems to be kind of this merger of loads where the earthquake takes over. These are almost all pancake collapses, even though they are in the inundation area. We're getting very low tsunami heights between 0.5 meters and 0, even at 10-meter resolution. And so we can postulate that perhaps in addition to the tsunami loads, we need to start thinking about combination disasters, like perhaps Sensei has been thinking about recently. And so this brings me to kind of what we learned and what we actually achieved here. And in terms of achievements, obviously, we are predicting a lot better than we did with the naive machine learning model, which is much better, especially because we can use all this engineering information and this probabilistic methodology to do engineering work, which is something that we'd like to do. And we can look at how to improve our methodology, sorry, our predictions by considering these mixed disaster demand parameters and test our hypotheses for better predictions down the line. And I guess I'd like to leave you with some takeaway messages about these probabilistic models that we developed, and especially how important it is to get the uncertainty into the model, and so that we can propagate this to the output and begin the engineering process, begin this this questioning of the model results and what we can and can't achieve, and so that we can inform stakeholders down the line and communities. Look, this area is perhaps at high risk, but there are some processes that we can't capture here. And so we can start doing the science about those areas. So yeah, I think I'll leave it there and we can talk more later.
Well, I think we have time for one question. Yes.
So the
The
fragility,
microphone, so everybody can hear.
so this fragility analysis, started in the earthquake world. So is that your next step to maybe combine in places where the earthquake and tsunami and, bring in the earthquake into your machine learning and have a combined result? And then also, would you look at places where there aren't earthquakes, but tsunamis to see how your models work kind of this kind?
Yes, precisely. And we did attempt just the earthquake merger already. Some of the problems there is that the measures of intensity of earthquakes tend to be quite coarse resolution, and we're trying to do very fine scale. And so the average maps of PTHA and that tend to be the general demand parameters that are used in seismic engineering don't quite work out of the box. So we need to think harder about how to upscale these. But yes, some other stuff that we like to look at is specifically Palu, because Palu is an example of well, there was an earthquake obviously, but then the majority of the damage was exacerbated by these subsurface landslides, which we'd like to really look at.
So we even have a time for a second question. Someone is interested.
Can you talk a little bit more about what intensity measure you use for this? Are you looking just at the amplitude, or do you use flow speed or maybe even momentum flux for this?
We just look at the inundation height, and the reason for that, and that's also the expedient for all the physical parameters that we're using, which I didn't speak about at all, but we had to develop in order to account for the loss of the momentum flux, because obviously, as I said earlier, when you have a building, there's a load on that building, and a portion of that load will be hydrodynamic and hydrostatic, and the inundation height really doesn't give you any of that. On the other side, you can't validate flux generally. I mean, I guess Koshi has done some video analysis for speeds, but the sampling frequency is so low that we can't really rely on that for intensity measures. So yeah, the challenge really was how can we add more descriptions of the environment in order to make up for the loss of the precision that would come from flux or force or velocity, because those demand parameters really do embed the processes that happen, perhaps not the directionality, but they do embed the processes that directly contribute to the damage. So yeah, so that is kind of like the limitation that we brought upon ourselves to try and fix.
I have a question also.
Yeah.
You were saying that the earthquake impacts, of course, is changing the situation when the tsunami is coming, but in the case of critical infrastructure where you have a well-established design for the earthquake, I guess the fragility curve for those conditions for the tsunami will be easier because you will have less uncertainty maybe because of the earthquake or not.
That is something we haven't looked at, but that's a really good question. Yes, probably. It would be, I guess, interesting to see whether the model can, the uncertainty is good right out of the box for measures for buildings like that. I don't assume so because we only disaggregate in terms of material, but maybe we can put some parameterization for things like that, like specifically buildings.
For example, bridges.
Yeah,
Yeah,
no, exactly.
perfect. Yes, run. We are running, but if it's quickly, just go.
I'll make
It's
it.
better to have the question
Yeah.
rather than keep it in the.
Okay, so one thing I've always wondered, Ruben, the Tohoku database, I think the building damage database has been very important for, for developing fragility models. And as you indicate, the parameter to measure the hazard intensity is essentially the maximum inundation depth. And most of your structures may be wood frame and so forth. I've always wondered whether using that maximum inundation depth was underestimate when you develop a fragility curve based on that parameter, whether you're underestimating the amount of damage that might occur through your fragility model. And the reason being is that it may be that a lower inundation level would have caused, the same damage or maybe severe and so forth. And so when you're taking that larger or higher height, I think maybe there needs to be some sort of scaling.
Yes, but you're completely right, and this is actually a question that I asked very early on in my research, and it's something that the uncertainty really kind of, we're really asking the uncertainty to do a lot of the heavy lifting in this. But if you know, it was a bit hard to see, I acknowledge that, but if you noticed in our last experiment, the probabilistic ones, you're correct. Most of the damage is underestimated. All the errors are underestimation rather than overestimation. And so, yes, that is completely correct. And so we probably do need to do some kind of correction there.
So thank you. Was really great. The second speaker, so we will introduce Katsu Goda here. He will do his presentation. Our microphone. This way. Okay, wonderful. So the button is working. Beautiful.
Yeah. Okay, so good afternoon. My name is Katsu Goda. I'm from Western University. And today, kind of the topic was kind of limited by constrained by the session like I'm assigned to. So fragility curve from hazard to risk, but half of the things is really to introduce what I have done for this Tofino, which you see a nice beach coastal town, touristic town in Canada, but facing this Cascadia subduction zone. And in the context of this fragility curves, I just wanted to just provide some sort of thoughtful ideas for discussion what can we do in the future? So I haven't done much work on those fragility curves themselves, but hopefully some of the things I mentioned might be useful. So that's the context. So in doing this probabilistic multi-hazard risk assessment by considering both earthquake shaking and then also tsunami, I emphasize put the emphasis for the long term. So not just for the next year or in 10 years, but we need to be looking at the century horizon. And then the Tofino is one of the most exposed location in Canada, facing this Cascadia subduction zone. And then so in this presentation, I'm gonna half of the talk will be current multi-hazard risk modeling and assessment done for this Tofino, also top down. And then some two specific topic. Many people are working, I believe, on the analytical fragility curve. So I have some thoughts on that. So I want to mention that. And then also potentially not just the building and infrastructure, but the fatality risk is really, really important. So what can we do analytical fragility modeling for fatality? So that's another things that I just wanted to mention. So I don't think I need to go into this Cascadia, the importance of the significance of this Cascadia for this group. So I'm just gonna skip. But just to point out, the Tofino is right on this, the middle part of the Vancouver Island. So and it directly faces the Cascadia, northern part of the Cascadia Arches. And then of course, the other hazard exists, such as storm surge, the storm itself, wind, and in the course of flooding. And also the sea level rise is expected to happen or is occurring. So the picture is very nice. So we have nice beaches, but those beaches are facing Pacific side. So in terms of this is the tsunami evacuation map developed by the district of Tofino. And then the Tofino town, which is around here, is kind of shaded, protected from direct tsunami waves from the Pacific side. And it's relatively on the higher elevation, more greater than 10 meters. So the less risk for this for commercial part of this town. However, we have a lot of beaches. You can see nice beaches here. So those are below 10 meters. And then they are prepared in a sense that you see tsunami sirens, and then the posting and so on. So an evacuation route has been kind of set up, and then they do annual evacuation drill. So together with the district of Tofino, I have done multi-hazard risk assessment for earthquake and tsunami. So I simply adopted the CAMP modeling approach. So by combining hazard exposure and then vulnerability, integrating everything as much as I can, taking into account the risk, uncertainty to evaluate the risk. And then for the Cascadia subduction part, I consider linear-based time-dependent seismic hazard occurrence model, and then also heterogeneous stochastic slip models. So that serves as the common effect for both shaking and then a tsunami. And then I independently go through ground motion simulation with spatial correlation and then seismic vulnerability function applied. And then on the side, tsunami inundation by solving the channel water nonlinear equation and then applying the existing tsunami fragility curve. And then by integrating all those, I can get to multi-hazard loss estimation. And in doing so, I just want to mention that the multi-hazard is, I say multi-hazard, but the ground motion risk is assessed for each building. And then the tsunami risk is evaluated for each building, but I just took the larger of the risk from either. Yeah? So depending on the location, sometimes seismic dominates, sometimes tsunami dominates. So I say multi-risk, but it's simplistic in that sense. And in addition to that, I currently add the cluster on the insula earthquake as well on the background, and then follows this ground motion modeling. And then I do the long-term simulation. So sea level rise and then also the tidal variation in a stochastic way is included in the model. So the reason why I chose this district phenol is that the very detailed building by building survey results were available. So we know exactly footprint, what's used, and how many people live, and so on, so on. So those are just the some example of the data we have in terms of exposure. And then the importance of this exposure data is very, very critical. If the exposure data is not good, then of course the final risk assessments are not that great. We also did the micro seismic zonation mapping for district of phenol. So we have a BS30 data for every, I think, 100 meter or so. So, but in terms of fragility, I use the Natural Resources of Canada's adopted open quake seismic risk assessment framework. So they specify the vulnerability model. So I adopt as suggested by the open quake. And then also for tsunami part, which is a fragility curve for the wood frame structures, I use the 2011 Tohoku earthquake fragility model. Partly because I still believe in the empirical data over the analytical data. But that's just my preference. So if we do those risk assessment, we can come up with so-called exceedance probability curve. And then the black curve is for the total multi-hazard. Multi-hazard in a sense that the cascaded abduction zone with shaking, with tsunami combined. And then on the background, we have non-cascadian shaking as well. So we see that the non-cascadian shaking is the blue, so it's not that dominant. The ground shaking, in fact, is the most dominant because it's very, very close to cascaded abduction zone. And then the inundation, tsunami risk is in red. But if we limit to the building less than 10 meters, then essentially shaking and then the tsunami are almost equal. So depending on how we take those exposure data set, the conclusion could be somewhat different. And if we take one particular, say, return period, say for Canada, 2,500 years return period level is very important because it's specified by the code. Then we can develop this kind of a multi-hazard map. So this is the dominant shake map, sorry, the slip, earthquake slip distribution. This is the shake map, and then the shaking damage. And then this is the tsunami inundation map, and then tsunami damage, and I combine those two by taking the larger of the two. And I mentioned that we can do the linear-based time-dependent modeling. So if the time elapses from now on, then gradually the occurrence chance for earthquake, cascade earthquake gradually increases. So the exceedance loss curve for different years is essentially shown. So we can gradually see that the risk increases across this 21st century. But in doing so, the one important thing I'm not including here is the exposure changes. So I believe that if we include the exposure changes over the century, this effect will be much, much significant. I don't know which way it goes, but it will be very different. And I mentioned that we take into account the sea level rise scenario. So I show exceedance loss curve for current situation. And then the 2100 at the end of this century. And then this red curves essentially showing the different RCP, representative concentration pathway scenarios. So in Canada, we consider 9 scenario. So at the present, which scenario we consider, essentially 9 curves are essentially the same. But depending on if at the end of this century, some of which pathway we consider might change to some extent, some differences. So with those results, I had an opportunity to talk to the people in District of Tofino, and we are developing a new kind of phase for research for Tofino. So those are the things that the list of the things that we want to do. in maybe 5 to 10 years period. So we take a disaster cycle as an approach, and then we identify some of the key action for each phases. And then I'm not saying that we can solve everything in one go, but one of the things could be solved, and then gradually those things might be ticked off. Okay, so just to mention a few things, ideas for fragility curve model development. So I think Ruben's presentation have essentially hinting that the analytical fragility curve is very established research field, at least in aspect engineering, and in fact that I'm from aspect engineering group by education, by training. So and then the one of the things, of course, that we can apply, and we have applied, is the main shock aftershock type. So if we have a main shock and we expect the multiple aftershock will happen, and if we apply the sequential ground motion to the building, then depending, of course, the intensity of the shaking, it will gradually decay. So we have developed the analytical fragility curve for relatively simple structure, for wood frame structures for Canada, to account for the gradual transition. If the building is precondition is not damaged, then the fragility curve for the collapse might be in this curve. But if the pre-damage is already happening, then the significant shift of the fragility curve might happen. So the same level of shaking might lead to more consequent, larger consequences. And we can definitely apply the same concept to earthquake and tsunami sequences. So in doing so, one, I think, missing component or challenging component is to come up with the time sequence, shaking sequence in time series, and the tsunami, whatever the wave height or whatever the velocity in time series. Because in the end, we might want to do the dynamic analysis of the building for analytical fragility modeling. So I don't have any particular solution or output to present here. But as a start, I looked at the Tohoku earthquake, and then we can apply for the ground motion simulation part. Of course, we can do the physics-based simulation, but we can also do a relatively simple, cheaper computationally stochastic finite fault method, but calibrated against the data. And then on the background, we can run tsunami simulation as well. So that kind of thing might be useful. Especially if we look at the coastal line like Diaz Coast location, which is the Shizugawa, heavy damage happened, about 15-meter height tsunami observed, or the coastal plain region, such as Iwanuma. And then we have developed the stochastic finite fault simulation model. So this is the observation actually at the Kipnet station. And we can simulate using that stochastic finite fault, say hundreds or thousands of those simulations. And then in terms of response spectrum, much is reasonable, as you can see. So those are the two examples for the two locations we have done. On the slide, we can simulate the tsunami. So we can get the wave height in time series, and we can, if we believe in, then we can calculate approximately as well. So those are the, and then we can combine those simulation, ground shaking, plus those inundation, and we can apply to tsunami fragility model. The other things I think it might be very useful is the fatality risk modeling. So for Tofino, we had very detailed exposure data, population data for house by house. So, and then we had some sort of temporal tourist population data as well. So, hypothetically, I simply used the Japanese fatality function, which is not necessarily applicable, I believe, I'm sure, for Cascadia or the Tofino, but there's no other model available. So anyway, I did it. Then we can combine that with the stochastic simulation to come up with the conditional fatality curve. And then if we combine that with the temporal aspect model, then essentially we can come up with exceedance loss curve for fatality. We can use this, potentially we can use those to discuss a lot of policy related things or evacuation. So that could be done, but another opportunity I see is that many people do evacuation modeling, and then especially agent-based modeling. So what if, so we did for Japan, we haven't done for Tofino, but whether we have evacuation tower or not might affect somewhat significantly the performance of the tsunami evacuation. So, but potentially this kind of evacuation model can be fed into those analytical fragility modeling for fatality. So this is my last slide, future plan. So at the moment, I'm working on the coupled stronger motion tsunami simulation for Cascadia. First, starting with the stochastic finite fault model, which is because it's easier and quicker. Then hopefully we are developing, we are working on the physics-based ground motion simulation as of later. Development of the multi-hazard fragility curve, not just shaking tsunami, but also aftershock, etc., is very interesting. And then the human fatality model by also taking into account the effect of the warning, evacuation, those are really interesting. And then the multi-hazard risk-based microzonation for policy making and the evacuation procedure. And then other ongoing hazard. And then by integrating those, we might be able to provide a lot of information for also communities. And then just my promotion, if I may. We just published the book on the probabilistic tsunami hazard and risk analysis. We are just the editor. There's a lot of eminent people who contributed to this book. So if you're interested, please have a look at the book. Thank you.
Okay, we have time for questions. So thank you guys. You were catching the time actually.
Yeah.
Okay, very good now. So question, yeah.
So finally, you mentioned something that development of multi-hazard politicals. So the question is related to this one. Your current loss estimation is based on the larger damage either by the earthquake or tsunami. So the simple question maybe is why not consider the cumulative damage? And furthermore, maybe the hard question is what's the challenges to develop the multi-hazard politicals?
Yeah, well, so I think that's coming back to the Ruben's kind of research as well. So we also find that the Noto earthquake might be a really good example for that, like especially the Ukai region. There's a mixed combination of the shaking damage and the tsunami damage happening. So I think that the fundamental limitation we have is that the data to calibrate. We can propose anything, but like my background is engineering, and I don't necessarily believe without any validation. So to do the validation, either Tohoku earthquake or, as he said, the Palu earthquake or this Noto earthquake, those are the things that could be used to see that how shaking and then the tsunami which dominated at which building level. So I think we need to go into that direction if we really want to develop this kind of approach. And I haven't done this, so I'm just putting the idea.
Yes, looking forward to it. That's because we know apparently in most cases, as 1 + 1 is bigger than 2, right? Because the earthquake comes first, and then it's destroys some buildings, and then you have damage, and then when tsunami, either the near field or far field, they reach and strike the building again, and then the damage can be more severe than expected, right? So apparently we had that, but I'm wondering if we can collect some emit data or do some surveys after some earthquake and tsunamis and to collect some data about the joint, we call the joint damage, and then to validate some predictors. So we were trying to develop. Yeah, thank you.
Question. You and then Ron.
Katsu, thank you for that. There's been other earthquakes and other tsunamis with damage. And so I wonder if you could comment on the viability, this is something that Shimura Sensei worked on the viability of using remote sensing identified damage inventories
Yeah.
as a way to validate this in Chile, in Indonesia in
Yeah,
two thousand four, and many other earthquakes.
Yeah, totally agree.
Bueno,
I just wanted to.
yeah, and while I'm working there, I also want.
Oh, yeah, no, go ahead.
No, I have something that you said before also, that we want to try to calibrate some kind of probabilistic model, but we are basing in one case.
Yeah.
So it's one sample
Mhm.
for a universal population, so that is another challenge actually for validation. I don't know if I did your.
No, actually, no, you just added on. Well, actually, I don't want to make a question, I want to comment, but I'll comment on that first because, yes, perhaps something that, because my brain really blanked earlier. But something I forgot to mention was about the Noto case being outside of distribution. In terms of even just the tsunami damage, the inundation is much lower. And the distributions are not the same for many of the parameters, and the fact that we still get something useful out of it is impressive. But I guess where I'm trying to get with this is that it would be optimal really to have a global data set for damage where we increase the distribution so much that we account for all the cases really. And I wanted to jump in a little bit on what Diego just commented about remote sensing damage states. One of the biggest challenges that we've had with kind of doing that is that a remote sensing generally just looks at the top of the building, and so a lot of the damage tends to be very biased towards the most damaged classes because that's where you really see the damage. But it's really hard to detect lateral damage or kind of like the blowout for a tsunami that's completely destroying a building except for the bones. That's really hard to do without obliques, and I think Bruno is cooking something interesting with that, trying to do some clever data fusion with both, and hopefully that goes somewhere because I'd love to see it.
Okay.
I think one of the other issues is distinguishing between damage and loss. Like a lot of the flooding from hurricanes is loss. There's no damage at all, no structural damage. It's just it just inundates the building and they lose. And I think for tsunamis as well, there's lots of areas where the intensity is not that high, but the flood depth is. So that, there's not much quote unquote damage, but the losses are high. So we need, like in addition to damage models, we need some way to connect to the loss.
So you talked about the need for the validation for like multi-hazard fragilities. So this is should be validated against the real data. So from the field investigation, how do you distinguish actually whether earthquake has damaged the structure or the tsunami has damaged the structure from the field investigation?
Well, I mean, like the marks are somewhat obvious, and then the shape and damage, like we look at the structures, right? And then the windows and so on. So, well, I mean, that's based on my experience, but like, it's hard to, I mean, I acknowledge that the data itself are uncertain and potentially biased. And then the damage states are not uniform across. So if Ruben said, or Diego said, that if we want to combine everything to make a global data set, then we need to have the same uniform somewhat definition. That's probably the start of the things, I think. Otherwise, we don't get to where we want to go in.
So.
I just wanted to validate, I think, one of your assumptions where you talked about how to reconcile damage from, from shaking, from tsunamis. And your solution was to take the one that it gave you the most damage. And I think that, it kind of makes sense, but I started saying, okay, well, why would you want to know what was the cause? Was it shaking or whether it was, tsunami? And I was just thinking, just right now, I said, you know what? When they have hurricanes, that's one of the problems they have, is that they have to distinguish between damage caused by wind or flood. And the reason being is that because, the entity that pays for the repair of that damage is either FEMA or insurance companies. And so it becomes very, very important. So that I may have changed my mind. Maybe there's another reason to try and refine, maybe that assessment of where the damage is caused.
Might affect the type of mitigation that.
That's right.
And the type of mitigation and design actually. So, yeah, let's go with the other question. Better to have question.
Well, I was right in line with my question or comment, just thinking about, how do you classify that? And when you were talking about looking at damages and using remote sensing, I'm curious, have you looked at places, years after an event that have pulled permits to either build a new or retrofit or design afterwards? And can that tell you something about the damage state based on either the permit that they pull, assuming that it's a place that has building permits and, uses those, but that might be a way that you could look at places that maybe don't have complete damage or that you're not as able to see it as easily from remote sensing or satellite imagery. Or maybe you already do that.
I just think this as a comment, yeah, I totally agree, that's important, like I don't have any solution answers to that.
Okay, thank you very much, Katsu. It's very interesting. Okay, so now time for the third presentation from Dan and Fabian.
Grab this one.
Okay, very good.
Hello.
So. There you are, very good.
Awesome. Everybody doing okay? Ready for more PowerPoint? Few more slides. So I'm Dan Cox, and I would want to acknowledge a lot of co-authors, especially Andre Barbosa. He's been a colleague of mine at Oregon State throughout this. We started about 10 years ago. Shafiq Mohammed, Mohammed's here. Young-Soo Park, his colleague now at the University of Hawaii. Dylan Sanderson, who's here twice because he did so much work. Kamesh Fabian. But we were funded by NIST, it's National Institute of Standards and Technology for risk-based community resilience center of excellence. So we're trying to look at resilience as the damage and recovery of communities in a risk-based sense. There's test beds in several parts of the country for tornadoes, hurricanes, earthquakes in the Midwest, and then we are kind of added as this multi-hazard piece here in the Northwest doing earthquakes and tsunamis. So this is just kind of a little snippet of some of the work that we were doing. And it was primarily for the development of an open source modeling framework called INCORE. So you're not going to see a whole lot of validation. In fact, you'll see no validation at all. But this is really useful just to get the model up and running and what are the different parts in this model and what are some of the uncertainties. So that was our challenge, not necessarily making predictions for the city of Seaside. But this is our poster child here. This is City of Seaside. And it felt like the Goldilocks kind of size community to work on. It wasn't too big, wasn't too small, had enough different types of the built environment in there. So we felt like this is the right size for us to work on. And I'll talk about how we are estimating risk. Before I get to that, I just want to talk a little bit about the probabilistic hazard tsunami. We didn't have any when we started, so we kind of rolled our own. We just made our own tsunami inundation. We used the NOAA model, and then we used Patlinet's cool wave, the Boost Nest model for the inundation. This is actually Newport, which we did a little bit later, but we also have another one for Seaside. Focused mostly on the inundation, and it was pure, Manning's End. We didn't look at any of the roughness elements. But one thing we did notice too is that in addition to free surface, the models automatically compute velocity. So this is a very important intensity measure to keep. So going forward as a community, it'll be really great to keep maximum velocity as an intensity measure, or momentum flux, and then some of the other things too, like just arrival time. These are also things that we can keep track of and, put some probabilities behind that. And then other things that may be useful that the models also can calculate fairly easily are things like duration of flooding. So if you're first responder, or you're worried about access of different roadways and stuff like that, you can use these models to also figure out, well, what's the probability that a certain section of roadway is going to be flooded by more than a meter or something like that, for how long. So I think we should do more than just free surface, is what I'm trying to say with these models. In addition to potentially looking at things like the joint correlation between free surface and velocity, or free surface and momentum flux. And this is more like an engineering perspective, like can we bound these by Froude number or something like that if you have to make back in the envelope calculations. But I think we should do a little bit more with some of the model output or joint distributions. This isn't on this, I don't have it on this slide, but things like the intensity measures for the tsunami versus intensity measures for the earthquake. So you can have PGV and freeze and depth. You can start to look at those statistics as well. And then we need to compare our stuff throughout, just see like how much progress are we making, how different things might be. So this was our first attempt at it. This was ASCE 16. This was one of the Dogami simulations. So depending on how much fidelity you need, you might just say, I forget to say like when can we stop? When is good enough? But I think we just need to keep track of that so we don't just keep modeling forever. I'll talk about Seaside again. I rotated it so you so it fits more on the page, but north is that way. So that's the Pacific Ocean. Tsunami is coming down here. You can already see some structure in the city. Yeah, the downtown. This is the beach where people are. This is the more concrete buildings and shops and hotels. Hotels are also right along the waterfront, and then these are all wood frame buildings. It's all wood frame on this side, and then there's more concrete back here, concrete and steel. So there's some more commercial, and then more residential, and then some critical infrastructure as well. So we talk about trying to create a digital twin, of the city. This is like digital second cousin twice removed. It's not a twin, but again, we start with nothing. And so we purchased a tax record. It has all of the different classifications. You can already see residential, commercial. They list a lot of things like number of, square footage, age of construction. There's tons of stuff in the tax record. Doesn't necessarily say it's made of concrete or wood, but you can make a pretty good guess after that. We also, ourselves, grad students, we do Google Street Through, just kind of go through and see, are we kind of close? And then also there's a very formal way of doing rapid visual screening. This is a FEMA tool for earthquakes. We kind of adopted that a little bit for tsunami. So in about a day with 6 people, we got like 12 buildings. You can't do a lot when you need thousands, but at least you can kind of spot check and see, if there are some critical things like hospitals and schools and that kind of stuff. You definitely can. And then we start to classify things by material, whether it's concrete, wood, or steel, how many floors, and then the seismic code, like how strong we think the building might be. And that's necessary for these fragility functions because they're classified by building type and so on. So if you have never seen fragility functions before, you can watch this. If you're a structural engineer, avert your eyes. It's gonna be pretty rude. But you basically pick out what type of building, concrete, like this hotel. So it's a 5-story hotel. It's made of concrete. It's built at a moderate seismic code. And then the inundation is telling us it's a 4 meter flow depth at that structure. if you were on the roof, would you survive? Would this thing collapse or not? You know, you could always ask that question. But from these fragility functions that were developed in Japan after their 2011 tsunami, reinforced concrete story, concrete building, 3 stories or higher, the probability of collapse about 10%. So, you know, probably I wouldn't recommend it, but you know, it would possibly be okay. Right next to it, though, is a wood frame building. You just select a different fragility curve for wood, and this is about 90% collapse. So, you know, these are very quick. You can do it probabilistically. You can paint the whole town if you want. You can do thousands of iterations. And that's what you get. You can also, like, you know, this has been done for decades with earthquakes. So you can do the earthquake separately. You can do the tsunami only. You'll see these are kind of like the photo inverse, if you will. The concrete suffers with the earthquake. The wood does pretty well. And then for the tsunami, it's the reverse. The wood does terrible. And then the concrete does okay. But then you have to combine them. You know, that's something we're just talking about. How would you combine them? And then how would you ultimately calculate the loss? So if you're working with tax records, you have some sense of the real market value. And then what is interesting for risk with the PTHA, now you have this probability of the event, right? You know, if it's a 100-year event, 5,000 or 10,000. And then with the fragility, you can get the consequence. So now you can estimate risk. So this is like getting down to worst case scenario. Everything is red, but it's pretty low probability. So it's not that high risk. And you know, the opposite at the top, it's much more likely to happen, but it's a low consequence event. So your risk is somewhere in, your highest risk is somewhere in there. And we can plot it this way. So it's kind of just turn 90 degrees. But if you look at your annualized economic risk for buildings in seaside, you would get a picture that looks like this. It's this black line here goes down. So this was like worst case scenario. You can also deaggregate it to see how much of that risk is from the earthquake and how much risk is from the tsunami. So for most of the buildings, they're really affected by something that's more likely to occur, this 250-year event. That's your worst risk because you have so much high value concrete waterfront property. But it doesn't matter if it's waterfront, but it's the hotels, the high rises, the things that, you know, have more dollars associated with it. And then for the tsunami, but when you get to about the 1,000-year event, that's where you start to see a lot more economic risk. And then you can combine the two. You can also do the same thing with the critical lifelines. So we also did the water network, the power, and the road network. So you have, you know, pipes, water pumps, water treatment, EPN, you have the power stations, poles, all that kind of stuff. And then with the road network, it's mostly just, you know, bridges and surface streets. But you can do the same thing. You can pull out the fragility functions from HAZUS, and you can do the exact same thing. You can see what's my peak risk, for example, the transportation network, and what is it more vulnerable to, the earthquake or the tsunami. In this case, it turns out that the bridges are really expensive, and they're most vulnerable to the tsunami in this case. So you're looking more at like the 1,000-year event. And then the water network, because it's all underground, it's vulnerable to the seismic piece of it. So you're closer to the 250. And you can also look at uncertainties around that. Like we're a lot more confident in estimating damage and loss of buildings, but not so much for the pipe networks. So that's one way to use these fragility functions. And again, you can use them, they're fast, they'll look up to. But there's a little bit more to the story. I want to add this thing. We, as I mentioned before, we had to do it ourselves. We just used the tax record. And so we built a twin, you know, a version of the city, you know, our best guess on it. But since then, there's the National Structures Inventory, which the Army Corps put together for HAZUS with a lot of other things added to it. So this is an awesome database. This is a national inventory for all of our buildings in the US. So if you re-ran it with the NSI, how would that compare to something like, let's say a local jurisdiction might have put together? And again, in this picture, you can already see with the same inundation, so the tsunami model is the same, the fragility functions are all the same. All I did was just pick a different description of the building stock. And you can start to see some things are very similar qualitatively, but when you start to get down to the parcel level, like how does this affect me, my building as an owner, you start to see a lot of variation. For example, here in the downtown core, you can start to see pretty big differences between major damage and minor damage. And then other parts, it looks pretty consistent. So I think this is just for me, a way to think about the other sources of uncertainty. We can't make one part perfect without worrying about some of these other inputs. And then at what point does it matter? Sorry for the blurriness on this one, but was our tax assessor data. This is NSI. This is looking at the block level. So it's a little bit more than just at the parcel scale. You're starting to aggregate things together. And as you go further from the shoreline, you have less damage. Go closer to the shoreline, you have higher damage. The dashed line here, this is perfect agreement. On average, it's not bad. You see a lot of scatter, but on average, it's not terrible. And then as you start to go out to like parcel scale, where you want to see like my house or my property, you start to see a lot more scatter, a lot more uncertainty, just based on how we classify buildings. If you go to block group and let's say you're the mayor, hey, I just want to know how the whole town is doing, then you expand out. It's not looking that bad. It wouldn't really matter which database you use. And then as you go in different mean recurrence intervals, you kind of get the same story. There's a little bit more nuance because when you get to higher and higher events, it just kind of blows everything out. So the uncertainty does go down a little bit. But that's just one piece, I think, trying to look at how we think we know the building stock affects estimating risk for communities. Got a little bit more time? Timekeeper?
1 minute.
Sure. Well, if you look at this picture, I wanted to talk about debris because one thing that's really interesting about these fragility functions is you can also use them to pick out how much debris you're going to get. So what's the percent damage? You know if it's concrete or wood, so you know if it's going to float. And now you can start to run some little bit more sophisticated inundation models. I'll skip the video. And you can start to move the debris around and get also some estimates of where you think the debris field might be and how it might affect things like the different roadway access to hospitals and things like that. So I think there's some other things that we could potentially pull out of the type of models that we're producing. A little bit more on life safety. We can also use them to show the value of retrofit. So again, you're just kind of moving to a different fragility function. So it's very easy to show the what if scenarios with these things. And I'll probably just stop with that, but I can go back to it later.
Thank you then. So we will keep a couple of minutes for question about this specific presentation, and then we will go into the round table.
Yeah, so I was wondering, did you figure out exactly what it was that caused the discrepancy between the tax parcel data and the NSI data? Like, I know Washington State had found some errors in it with like the number of floors. And I work for FEMA and I talked to the team that deals with like, the NSI on our end and everything. So they're always very interested in what was wrong.
Yeah, it is things like a misclassification, misclassification, but yeah, like whether the building was made of wood or concrete, the number of stories is different. We're spending a lot of time on hurricanes now. The elevation is oftentimes incorrect. So I think good news is when we aggregate, and we kind of add everything together. It's not that bad. It's just that people, I think we have to be very careful if we're doing like more personalized risk and you want to show this to the general public, because the first thing they're going to see is what, you know, what about my house?
What's my house?
Yeah.
Valerie, question first.
Yeah, maybe similar to the last question, but I'm curious if you have thoughts on why, maybe you mentioned this, the NSI tends to predict more damage than the tax assessor.
I don't know why, no.
I was gonna comment on your question, because we have been working in Washington, you know, with our example. And we Maximilian Dixon was kind enough to share the data that they had collected, you know, with their field work, and to compare it with the NSI database. And I'm going to talk about that if I have time in my presentation. But, you know, there's obvious things like, for example, they may miss things that don't necessarily look like buildings, like marine facilities and so forth. They will overcount things like outbuildings, you know, that you normally would extract. And then there's some of these imagery artifacts where, you know, it looks like two buildings, but it, you know, it's one building, but they count it twice. And so there are a lot of things like that, but, you know, your point, Dan, if you look at the overall, you know, sort of community, you're probably not going to be that far off. But, you know, you want to be able to at least, you know, provide confidence that the data that you're using, you know, reflects, you know, an accurate database. And I think that, you know, there's some work there. But, you know, remote sensing also is another aspect of creating, especially data in emerging countries, you know, where you don't have tax assessor information and so forth. So.
What about the effectiveness of this exercise you did with your student of going for street by street, and just by looking at the front part of the construction, it was giving you some accuracy, to gain accuracy?
I think it gives you more confidence in what you've done. So, you know, we just use the tax assessor data for thousands of buildings, and then we spot check them. You know, does it look right? We've since used it for that. This is more for hurricanes, but we spend a lot of time on the damage analysis. So we do a street view after hurricanes, and then we do like 360 view and that kind of stuff. It's very, very time consuming. And I think ultimately that'll be done by AI, but we feel like we can make some training sets or something like that. But one of the hardest parts is, yeah, that for some of the elevated structures, like even parking garages and stuff like that, they want it to look nice. So it looks almost like fake windows and stuff like that. It's really just an elevated building. So it's easy for untrained eye, myself included, like it just looks like first finished floor, but it's really an elevated structure. So I think sometimes we need to work maybe a little more with practitioners on like what constitutes a real first floor.
Hi, David Goldblum-Helsner, U.S. Environmental Protection Agency. Dan, great presentation. I was saying that you curious how in the debris area that you actually went as far as looking at debris. One complication that I've seen is that debris can also act as impacts on buildings themselves, like even just seeing that ship over there. And it also could you know, take bridges out and other types of things that may not have been out. That's one thing. The other thing, underground, you can get scouring of the from tsunamis to reveal pipes, water pipes, gas pipes, and that infrastructure could be also taken down.
Yeah, that's a great point. So our analysis had no scouring in it at all. We were just looking at, so that's why it's mostly seismic, but yeah, that's a great point. And the debris impact, I think there's definitely a lot of researchers, Pat Lynette, for example, at USC, looking at kind of a probabilistic model. If you're a building, what's the probability of debris hitting you? Or if you're a shipping container yard, what's the probability of those containers being somewhere else? So kind of in both directions. A very active area of research for sure.
So Well, we will jump into the round table, but we have time for one question. Who wants to question? Yeah, go ahead, what's your question? And then we jump into the round table.
I think this kind of goes into the direction of when do we stop modeling, but are there any attributes that you don't have the data for, but you're curious about? Like, I'm curious about fire for the earthquake piece and what other things can get added in that we just don't have the data for.
Yeah, I think that's a big one, fire following tsunami for sure. I think Nobu Mori in Japan, I saw one paper that he put together. I think the probability, again, this is low probability but high consequence. If we were to have an event on the 4th of July in Seaside, that's totally different. Or what if it's a pouring rain January night, then what happens to those displaced people? So I think looking at some of those outliers might be important too. Even though they're low probability, it probably would be worth looking into.
Okay, so now we will open this session of roundtable. So for this specific session, we have this question. So of course, it's up to you if we keep going with this question, but for sure we want to know what is your perspective about this session. So these are the 3 questions. So I will open now the microphone to anyone who have a question or comment related to the presentation, or even far about fragility analysis. Huh? The early career, sorry. I forgot even my own instruction. So first of all, let's try to give the space to early careers to provide questions or comments about this topic. So go ahead, please. Early careers. I want to see your faces. That is why you come here. So, Ruben, very nice, of course. All the early careers as well. Only Ruben.
I mean, I wanted to ask a question about the debris actually, because we try to proxy the debris by using the number of wooden buildings in the calculated beams. I think this is research dating back to the ancient ages of last year, where I don't know if you're familiar with Mario di Bacco in Italy. No, they did. They calculated the distance between the coast and a building, constructed a rhomboid, and calculated for each building how many buildings in that rhomboid would be, and they kind of all the wooden buildings, they assigned a high probability of debris. And so we try to approximate it like that, but we never actually considered the road blockage and the debris field kind of blocking roads, and I guess that's fairly useful for rescue operations and kind of post-event logistics. I guess my question is, do you see specific trends in how these move, and does the model affect kind of the dynamics of where the debris field ends up? And is there some uncertainty or the variability in the location? Like, is it wildly different, or?
Who would like to provide?
I can answer real quick. So we went kind of backwards. We looked at observed debris patterns after Japan, and you see like the rack lines, and same with hurricane, you see all the debris pushing up here. And so we said, what would we have to put in our model to make that happen? And there were 2 things. One was a threshold of movement where the debris would start to move, and a threshold where it would stop moving based on depth. If we didn't have those, all the debris does is follow the water in and out, and the debris is over there. So it's kind of like, what modeling would we need to do to be able to get the debris to look like what we saw in Japan? And then now let's let it go. So, and then we played with those 2 parameters. It's a little bit like sediment transport. You have like a critical threshold. So we were just playing around just to see if we can get the debris to move, and can we move thousands and thousands of pieces. There's people that can do like a shipping container yard very carefully, but there's only a few hundred. We want to think like, well, how would you do thousands, millions of pieces? So very simple rules, and then you just have a particle tracking model.
So you did use a polygraph. Oh,
This,
thank you.
Yeah, I remember I did something similar. Okay, more question.
Thank you for the presentation, Dan and Professor Goda. My question is about, have you seen any kind of implementation of these kind of damage maps or fragility models into or informing like the disaster response strategies? Like, I don't know, where the city is going to locate new fire stations, or where they are going to, how they are going to approach the disaster in terms of urban search and rescue, any kind of approximation that way, like any kind of informing strategies.
Okay.
So JPAD and California Geological Survey, we are using structural reliability analysis, basically fragility, structure for developing tsunami hazard zones. And so using the structural reliability analysis that Pat Lynette developed to choose a return period for the basis of the spatial extent of these hazard zones that will, much like we have active fault zones that are regulatory zones for required investigation. And so we're developing hazard zones for tsunami, and the return period, we're using the return period based on this reliability analysis. And that's actually, when I first started working at CGS, we had an advisory panel that we developed to help us decide what return period to use for our evacuation maps or tsunami hazard area maps. And I realized soon that no one really has a method of choosing a return period for hazards. There is really no method, but then Pat Lynette presented the structural reliability analysis, and I realized, well, this is actually a way you could quasi-quantitatively make a more objectively chosen level of return period for your hazards. So this is really probably the most exciting thing, I think, development of tsunami hazards is this fragility analysis, because they've been using it in earthquake hazards, seismic hazards, but it hasn't been applied for tsunami hazards. Because right now, it's basically, well, should we use 975 or 2475? And there's really no basis for making that decision. It's 100% subjective, but this fragility analysis, structural reliability analysis is a way of getting to that. But don't ask me to explain it. No.
Any comments? Early careers?
I'm curious about how these types of results will be communicated with communities. Like, will it ever be on the building by building scale, or is it always going to be kind of like a citywide assessment? I'm thinking about like actually going there and showing this type of data to people.
So we made the decision not to show it at a building by building basis because that's going to cause problems. So what we do is we smear the results across census block areas and things like that to present, damage states, fatality estimates, things like that. So we're purposely avoiding getting down to the individual building. I mean, the reality is there's also a lot of uncertainty in these types of estimates. So we don't want to be presenting something as fact.
I have a question that kind of follows that up, but from the other side of the perspective. So you showed us, some concrete structures that might be good places to go on the roof of, but might be marginal, et cetera. And of course, we have a almost total lack of actual vertical evacuation structures that are sort of vetted or purpose-built in our whole region. I've been to places in Japan where every coastal building is a vertical evacuation structure and labeled as such practically, or many of them are. So would there be any way to use this use criteria to actually identify which buildings are reasonable ones for people to evacuate in place as opposed to try to head for the hills? Is that in the future for our coastal communities in Cascadia, or is that a long way out still from existing infrastructure as well as things we can purpose build in the future?
So maybe John, you can follow up and then we'll go with you, because I think it's interesting about this.
So that's a great question, Harold. So in the town of Seaside, actually 10 years ago, I think it was, George Priest and others actually were, evaluating this exact topic, working with the local hotel industry to identify potential sites that were, multi-stories, more than 5 or greater, that could be used for vertical evacuation. And they did actually identify one particular building that could be used for that purpose. The problem is that there's always concern about liability. And then there's also concern about, getting access up to those floors through secure, hotel doors and things like that. So there's some problems there that, need to be resolved. And so I don't think it's certainly not in our case, it's not the Garcia way of resolving this problem. I think we still have to look at eventually moving towards vertical evacuation structures, dedicated structures in certain communities. And there's another challenge actually in that respect, is that, on the Oregon coast, I don't know whether it's the same in Washington state, but there are actually height restrictions in most coastal communities. And so there are future needs to, provide legislation or planning guidance for getting over those types of questions as well.
Yeah, I was just gonna add, because we have talked about this a lot through the National Tsunami Hazard Mitigation Program about, do we look into refuges of last resort, which is what those are referred to as? Is that something that on the state level or the national level, we look into kind of initiating, or is it by a community? And I think the general consensus has been like, you're not gonna have a state agency putting themselves out there for, liability wise, saying, yeah, you can climb up to the top of this hotel and you'll be fine. Or even, we can't say that you'll be fine, but we are still saying that you should do this if you have nothing else to get to, because that still makes us liable. And John's right, I mean, there's nothing on our outer coast that is going to be tall enough, at least for what we model to. So yeah, in a one-on-one conversation with someone in, on the Long Beach Peninsula, if they're like, seriously though, like the waves coming at me, where do I go? I might be like, I would probably run up to the top of the roof of the Chautauqua Lodge too. But we have to recognize that like that truly is a last resort. And the thing that is difficult is that the more we push refuges of last resort, the more we look into them, the more people the public tends to not support vertical evacuation, because what they don't want, what they don't want is to have to build a new, very expensive, potentially, not the prettiest thing in the world, structure in their community. Especially if it is a place like Long Beach or Ocean Shores, where we're also going to tell them, you actually need like 18 of these, and each one is going to be $15 million. So if there's an easier way out, like, oh, we can just tell people to run to the top of the convention center, that's what they're going to do. So as much as that may have to be the option in the moment, we don't really want to tell them that, because then that's going to be the default. And what we need is that community push for vertical evacuation, because there's just nothing else that's going to do it in those communities.
Yeah, I just want to complete an idea of a participant who is not here. We were talking about how we can try to transmit the information about all what we are doing to individuals, so we can justify if someone really want to do the investment and try to reduce the risk for a tsunami. But then that thing that it was given by Gary Chok actually a week ago is in a certain way in conflict with this idea that we were saying that actually we are deciding even not informing individually about this tsunami risk. You see? So that is actually a very important kind of conflict in terms of like how we will informing people. Because maybe someone have the money and really they want to try to reduce the risk for a tsunami, but how? So it's a very important problem actually. Yeah. So, Robert?
I have a very, very stupid question, because I don't know much about fragility analysis. So if I look at the graphs that were shown, it was always like probability versus value of something or loss. And the loss was given in a linear scale in billions or whatever. Why not give it as a log scale? Because it is sort of a scale invariant problem, right? And then sort of like allocation. And then also, if you compare, let's say, 1 billion Canadian dollars versus $500 million, that's a ton of money. But if you go lower, then it becomes interested for the individual or town, because I can imagine that someone else is going to pay for the $10,000 or $1 million versus hundreds of millions of dollars. So why not do this analysis on the log scale of the value? What happens to the probabilities? Are they just not smooth enough up there when you do it in scale? Like on a like, are they just starting to oscillate or something? Why are we not doing this on a more meaningful scale for like interpretation of this, at least from my weird brain?
I think maybe just adding, is it on? Yep, maybe adding to it too is like, why do we put dollars on it? We could also put like the percent value of my total asset in it, so that it's less, the wealthier hotels become like the driving force. It can also just be like overall, you know, this is getting more to disaster equity, like just looking at the overall community's value being in that place. So I think we do need different things on the y-axis, not just annualized losses.
Just a comment about the vertical evacuation structures. When I was doing work in Sumatra, one of the things that came up often is that there's a lot of community resistance to vertical evacuation structures for similar reasons, cost and sort of trustworthiness. People were uncertain whether they would trust the structures, and also, you know, sort of the appearance of it in their community. But in that particular region, one thing that was surfaced as a really effective possible option is if the building was a mosque, then people would both trust the station more and they would be more interested in having it in their community. So, you know, maybe there are ways, if you're facing resistance from Seaside or whatever, maybe they would rather have a convention center or a new hotel that is also certified as a vertical evacuation structure, rather than saying we need to build a purpose-built, single-purpose evacuation structure.
So communities are actually doing that. They're thinking of these structures as multi-purpose, because that's the way to sell them. So in the case of Seaside, they had a major parking issue in Tikasam. There are thousands and thousands of people that come out here, and so they've got a problem. So they can build a multi-story parking structure and use vertical evacuation up on top. So they're definitely thinking about it.
The problem though, I'm looking at Kara. No, it's not your fault. The problem though is that the vast majority of these structures are going to be built with FEMA funding, and FEMA will not fund the multi-use part of the structures. So if you've got the funds, or if you're already building your police station and you want it in the inundation zone, and you want to tack on an extra, $3 million to also make it a VES, that's awesome. And that's totally what my program really tries to push in our local communities. And we have Acosta Elementary, the first VES, it is an elementary school, it's totally multi-use. But it's not the easiest way to do things, because if you want to build a parking garage or something, you have to pony up most of the cost of whatever that building is. And then the vertical evacuation structure cost is just whatever else it would be on top.
It's actually a lot more than that, because it goes from, I think, risk category 1 to risk category 4. So suddenly it's like cost per square foot of a hospital. So the parking garage, they'll never pay for it.
So I think this is a really healthy discussion, very healthy dialogue. And, you know, I think we all understand, you know, there are challenges, you know, there are issues, impediments and so forth that kind of stop us, you know, from taking the next step, whatever that step is. So I think the real question is there the appetite, you know, for decision makers to want to have the right set of tools to be able to examine, you know, what the outcomes might be for, you know, because a lot of people, you know, they talk about, okay, what are the benefits and what are the costs and how do I compare these sorts of things? I don't think that the tools are out there to be able to help at least inform decision makers that, you know, you've got a huge problem, or you've got a problem that may be manageable, you got a problem that shouldn't be a problem. And that's what I think this, you know, this workshop here is doing a very good job in sort of laying out and teasing out a lot of these issues. But the real question is, you know, do decision makers have the appetite to be handed a tool that says, okay, you know, you can use this tool to look at the, you know, these different options, alternatives, you know, are you, is the appetite there for that?
I would say kind of a resounding hell yeah. It depends on the community, of course, but if I'm just thinking of our outer coast communities who have known for a long time that they have this risk and that they need to do something about it, and they just maybe don't know what, or they don't know exactly what that risk is. There is a lot of appetite for more data or for different data, for, you know, debris modeling, for sediment analysis, for all of these things that can tell them more than just you're in the inundation zone and it's going to be bad. The more information they have, the more they can plan. And the more information they have, the more they can go for grant funding, which is absolutely huge at the state level and at the local level. You know, if they can say, not only, you know, do we know we have this many people in the inundation zone and it's, you know, it's going to be deep and it's going to be bad, but you know, these are the areas that are going to be hardest hit, and we're going to have, we're going to have debris that's potentially impacting roads out, or we know these bridges are going to be down. Anything like that that can more accurately express what that post-tsunami situation is going to be like is really helpful, because I think especially the higher up decision makers, the folks who, you know, are signing off the checks and things like that, they don't really have a great understanding of what that tsunami disaster looks like. I mean, we can show them pictures from Tohoku and we can say that's what it's going to look like here, but it's too far away in our history now, sadly, for them to really think it's going to happen here. And tsunamis are such a low probability event that, you know, things like wildfires and winter storms are competing every year. So we have to give like really good hard data that they can kind of be like, okay, I can get my mind around this. So any new models or new ways of looking at that data or of helping folks understand it, you know, so we can show it visually, or we can, you know, show it as a simulation or a video, something that kind of captures people's attention in a new way is really, really valuable.
I was just going to add, so case study Seaside, and Dan showed a beautiful image looking over the city of Seaside there. And if you notice, there's a couple of creeks that you got to cross if you want to get to high ground, which is in that image. It was down to the south or bottom of the screen, but to the east. And so it turns out that, you know, over the last 20 years or so, the city of Seaside has been debating retrofitting their bridges to allow for better evacuation potential out of the main block area, which is closest to the beach. Well, it turns out that if you do evacuation modeling and you retrofit all those bridges, you're only saving about 500 people, because they've got so far to go to get to high ground. But if you start to put strategically a few vertical evacuation structures at key locations, you can potentially save thousands of people. So that's kind of the cost benefit types of analyses that, you know, we're doing, other communities are doing, consultants are doing, in order to help those communities make decisions. Similar sort of study was done in Cannon Beach, and in that case there, it turns out the bridge is very important. And so by having the evidence that we can provide, they can then go to FEMA and make their case that we need to retrofit this building. So more data is definitely very valuable.
So we are running out of time, by far or not? Yeah.
5 minutes.
Okay, 5 minutes, okay, yeah.
5 minutes.
So the thing is that we will have a roundtable tomorrow, in which we can collect more information. If you have comments right now, we can keep it for tomorrow, where we can talk about all these things again. But we are running out of time, so it's better to move ahead because we still have another session and other events. So sorry about this. So what we will do now is jump into the.
We're gonna take a break.
Okay, good.